So, what is the rate law? The rate law is an expression that relates the rate of a reaction to the concentration of the reactants. In a double replacement reaction, two substances react to give the products. So if we can see a double replacement reaction, we see two reactants, we see bonds breaking, new bonds being made, and those new bonds are forming two products, correct? Well, with the rate law, let's say that we just have A, little a, little b, little c, little d. Bless you again. Now, what does that mean? What do those little a's mean? Those little a's, the little letters, are the coefficients in front of the compound. So the little letter would be a number in front of the compound. The capital letters would be the actual compounds themselves. I'll explain it a little more. You'll see it a little bit better here coming up. For a one-step reaction of A with B, the rate of reaction is dependent on the concentrations of both A and B. We know, we decided, we said before, that if we have higher concentrations, we have more collisions. More collisions equal faster reactions. So concentration does matter. Absolutely. Concentration does matter. So for a one-step reaction of A with B, the rate is going to equal a constant, which is letter K, that makes it a constant. And these brackets right here around the A, that simply states the concentration of A. So when we see a bracket, A, we read that as concentration of A. So what could a concentration be? Well, we've dealt with 0.5 molar substances, haven't we? I'm going to do a lab today as a demo for my other chem classes. They're behind you guys. They're on their double periods now. But we're going to do a lab with 6 molar hydrochloric acid. And remember, I said that's a very concentrated hydrochloric acid. Okay? So those right there are concentrations, and that is what these mean. The concentration of substance A, the concentration of substance B. And you can see that the lowercase numbers, letters, the lowercase letters, little a and little b, I told you those were the coefficients. So the rate law is K times the concentration of A to the A, little a power. Concentration of B to the little b power. So let's talk a little bit about K. K is the specific rate constant. It is a proportionality constant relating the concentration of reactants to the rate of the reaction. So K is the specific rate constant. It is a proportional constant relating the concentrations of the reactions or the reactants to the rate of the reaction. Now, in order to look at these things, we have to look at reaction mechanisms. In an elementary reaction, the simplest, that's why they call it the simplest, it's an elementary reaction. In elementary reactions, reactants are converted to products in a single step. So it's a reaction that occurs in one step. This type of a reaction has only one activated complex. Has only one activated complex. However, most chemical reactions are not accomplished in a single step. Most chemical reactions have a number of elementary reactions involved to make that final product. So how would you be able to tell whether something has a single elementary reaction or whether something is a number of elementary reactions? Well, you look to try to find how many activated complexes you would have. How do you find that? Well, if you remember, okay, activated complex were the peak of the activation energy. So how many hills do you have? If you look at a chemical reaction and see a bunch of different hills, you can say, oh, that takes a lot of elementary reactions. So when we get to these more complex reactions, we have to include all of the elementary reactions that are occurring. This results in a number of hills and valleys. The hills represent the activation energy needed for that particular part of the reaction, for that particular elementary reaction. So as we see these hills and valleys, we see many different activated complexes, many different transition states. And the valleys correspond to intermediate products. To intermediate products. Now, what is an intermediate product, though? What is an intermediate product? We'll discuss that in a couple of slides here. Okay? But I'm going to flash this next slide. I'm going to give you a second here to draw it. Okay. It's a little bit blurry there. All right, so let's look at this right here. Here is my reactants. Here are my reactants. 2NO plus 2 molecules of hydrogen. The final product, once I get that, is going to be a molecule of nitrogen and 2 water molecules. But in order to proceed with this reaction, I have how many elementary reactions? 1, 2, 3. So I have 3 elementary reactions that occur for this one reaction to happen. And what I have at my valleys here and here are what we call intermediates. Okay? So if I follow through this reaction, okay, I have my reactants. We need a little bit of energy, and then I form the intermediates, dinitrogen trioxide and hydrogen gas. Then I need some more energy to form my second group of intermediates, okay, dinitrogen monoxide, water, and hydrogen gas. And then finally, we have more energy needed to reach to my final products, which are nitrogen gas, N2, and 2 molecules of water. So this particular reaction occurs in 3 elementary steps. 3 elementary steps. Once again, how do I tell that? How do I tell how many elementary reactions are there? Yeah, I count the activated complexes, which correspond to the hills. Correspond to the hills. Now, we talked about these intermediates. Let's get a definition. An intermediate is a product of a reaction that immediately becomes a reactant of another reaction. Now, some details about an intermediate reaction. They have a significant lifetime compared to an activated complex. Now, I don't want you to be mistaken here, okay? I don't want you to be mistaken here, because how long did we say that something stays in the activated complex state, in the transition state? What was it? 10 to the minus, I think 13, right? So that's a very, 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 very small amount of time. So would 0.001 seconds be a significant amount of time compared to 10 to the minus 13? Absolutely. So this still can be a small amount of time, but compared to that lifetime of the activated complex, they are more significant. They have actual ionic or molecular structures. They have actual ionic or molecular structures, and they have some stability. They have some stability. But their final goal is to go on to react to give the final product. Yeah, Garrett. Do you see at the very end the results of the last, where it would have been, it comes off the last activated complex and goes down? That one was labeled products. Okay? So if you look at your diagram, go back and look at your diagram. Okay? You have hill. Let me go back. I guess I can go back here. Okay? I have hill, intermediate, right? Another hill, intermediate. Another hill, but this is my last hill, so this is product. All right? Now, I'm going to show you a chemical reaction here. And you can see, because that's the next slides. Maybe this will help too. Okay? Here is one elementary reaction. Here is a second elementary reaction. And if you and I were going to write this particular reaction on a piece of paper, we would write it like that. So, if we were writing this reaction, and this obviously is what type of a reaction? What type of reaction is this? A decomposition reaction. It's breaking down. It's breaking down a compound into its substituent elements. We would only write this part. So does my balanced chemical equation tell me anything about the reaction mechanism? Does it tell me how many steps it took to do that? No. It doesn't tell you anything about the reaction mechanism. All it tells you is reactants and products. Now, how many elementary reactions were required to get to this reaction? 2. Now, read to me, Ethan, what you wrote down an intermediate is. What is a product of a reaction in this one that immediately became a reactant in the next reaction? Right here. Right? So that is an intermediate. Oxygen would be considered an intermediate right here. Does that ever show in this reaction that oxygen's an intermediate? No, because we don't see the mechanisms. So that's something that a balanced equation will not tell us. Okay? So in this case, can we actually tell intermediates and steps? No. That's something I want to hammer down to you, that a balanced chemical equation does not tell you anything about the intermediates and the reaction mechanisms. Okay? Now, I think the next slide, okay, I guess we got more here. The oxygen atoms are intermediates. No, that's just what I was hammering down there. That the overall chemical reaction gives no information about the different mechanisms that are involved as that reaction proceeds along. Now, just looking at our time